Greetings, welcome. Hopefully you enjoyed listening to me eat a piece of candy at the end of the last video. So that was amazing. I really don't feel like doing these videos over again because of that. Oh well, so here we have, this is just a box on a ramp. The old box on a ramp, and it's just sitting there. So the free body diagram would be the force of gravity pointing down, and then there's a normal force like this pointing perpendicular to the surface, right? So that's a 90-degree angle. And then we would have a force of friction here pointing up the open. There's nothing here. This is a mistake. No. Nothing there. Right. So now we want to derive an equation for the normal force. So the net force in the y direction is equal to the mass times the acceleration in the y direction. So what's happening here is basically this force of gravity has got components. And I lost my camera, so I don't even know if you can see this. There we go. All right. So the force of gravity has got components here. And so, right, this is like the hypotenuse, and this is an angle here. Well, you could use trigonometry to discover that these angles are equal. And if these angles are equal, then this component down here is the sine component, FG sine of theta, and this component over here is the cosine component. Right, so basically what that means is if this is in equilibrium, if it's balanced, if it's not moving, then the normal force is minus the cosine component of the force of gravity is equal to ma, but a is 0. It's not moving. Right, so this is just basically 0. That means the normal force is equal to the weight times the cosine of the angle. Over here, Angela and Carlos gather some data. They measure the normal force and the angle in degrees, and what would you graph then? So if the normal force is equal to mg times the cosine of theta, and we have theta, so what you would graph, so this looks like, right, y equals mx. That's a slope-intercept form, a straight line, and so that's what you want to graph is, since the cosine of the angle, so that's the formula we had, so that's what we're going to graph. This on the y-axis, this on the x-axis, this will be the slope of the line. All right, so I've answered that question here. The physical meaning of the slope is the weight. The weight is the, this is the, right, plus b, 0, because when the angle is 0, I guess the normal force is, it's not at an angle, it's, it would be the cosine of 0. So, all right, there you go. I forgot to set the timer, but that felt like that went really fast. So let's try I. Alright, so on I, we have a car. We're going to draw a free body diagram. So it's just moving. So we have a force of gravity. We have an equal and opposite normal force, although those are not action-reaction pairs. And we have a force of friction. And it's sliding on the roadway locking, so there's no more engine pushing, right? So, does the value of d, the stopping distance, increase or decrease with increasing initial speed? It would increase, right? Because d is equal to the initial speed in the x direction times time. So if this increased, that would increase. Does the value of d increase or decrease with increasing coefficient of friction? So that would decrease. As the coefficient of friction increases, the force of friction would increase, and I think that's just kind of an intuitive thing. More friction, it would stop you faster. The road were stickier. And here's the end of it. All right, so we're going to derive an equation. expression of Newton's second law using m, g, a, and mu and physical constants is appropriate for each line. Explain mathematically what was done. The first line is done as an example. So in the y direction, the normal force equals force of gravity because ay is equal to 0. Okay. In the x direction is equal to m times ax, right? And the x direction, the only force is the force of friction, so that's equal to m ax. And force of friction is equal to mu times the normal force, max. And the normal force is equal to mg in this case, times the cosine of theta, which theta is 0, so it's just 1, equals m ax. So it looks like the mass on each side cancels, so the acceleration in the x direction is equal to mu g. And then for part D, there's a part D? Write an equation for D in terms of v naught, g, and mu. We have v squared equals v naught squared plus 2ax. So the final velocity is 0 because it screeches to a halt, and we have initial velocity squared plus 2 times, so a is minus mu g, and d is equal to d, or x is equal to d. So d, the distance, stopping distance, is equal to the square of the velocity divided by 2 mu g. How does your equation in part D support your reasoning about the relationships? Oh yeah, so we said before that if we increase the speed, we would increase the stopping distance. These are both on top, so as this increases by the square though, so you're really going to increase your distance that it takes to stop. If you double your speed, it's 4 times longer to stop. And how does changing mu? So if mu increases, the coefficient, the stickiness of the road, if this is on the bottom and it increases, that makes that lower. But speed is going to rule. All right, thank you. Let me see if I can actually click done this time.